Alright, on to our next exercise. So basically what we're doing is we're just figuring out how to set up this this matrix, these matrices for these systems of equations. So let's see here. In the text, remember we have a similar system of equations that we set up, and there we set VI to be the matrix VI1 and all the way up to VI n-1 transpose. So this was a column vector, and for each I, this gave us all the we fixed the first subscript and changed the second subscript. But here we will set Vj equal to the vector V1j through Vm-1j transpose. So here it's the first coordinate that change. It's the first sub-index that changes rather than the second. And likewise, we set Fj as a vector will be Fj1 through Fj. No, I have this backwards. Yeah, this should be this should match what we have for this particular problem. So it's F1j through F and then m-1j transpose. Recall that our systems, or that our equations are, and then I'm just going to remind you what it looks like here. So let's see here, we have minus vi minus 1j plus, well, actually, I'm going to write this separately. I'm going to combine all the terms. So it's going to be minus 1 over hx squared times, so minus 1 over hx squared times vi minus 1j. Then we subtract 1 over hx squared vi plus 1j. Then we subtract 1 over hy squared Vij minus 1, and then we have the same term but with Vij plus 1. And then we add the term for Vij, and that's going to be, we have a 2 over hx squared plus 2 over hy squared, and then we add sigma because of the additional sigma term, Vij, and this is all equal to Fij. And we have V10 equal V. So this is how we deal with the endpoints. Vi0 equals Vin equals V0j equals Vmj equals 0 for I between 1 and m. I mean, I guess that it's technically m minus 1 because when I equals m, it doesn't matter. Because that's taken care of by the other case. And then we have j between 1 and n minus 1. So we're going to define some constants, and then we're going to use those constants to set up our matrix. So alpha is going to be 2 over hx squared plus 2 over hy squared plus sigma bx equals negative 1 over hx squared, and b beta y is negative 1 over hy squared. Our matrix is then given by, so here we have a separate process that I'm going to go through for how to figure out what matrix to use. So we know the variables are going to be all the Vij's. And we're going to write it as V1, V2 through Vn minus 1. Right. V1 through Vn minus 1, and each of those Vi, or each of those Vj's is a vector itself, which consists of V1j through Vm minus 1j. So let's see here. If we just write these variables out, this is just how I like to do it. So I'm going to write it as V11, and that we're going to go all the way up to Vm minus 1, 1. So that's going to be the first vector. The second vector is going to be V12, and then V22, all the way up to Vm minus 1, 2. Then the next vector, we're going to have V1, 3, all the way up to Vm minus 1, 3. And let's see here. I actually want to give myself a little bit more room. So I'm going to expand this a little bit. All right. And that's going to go on and on and on. So that's just what we're going to have going across the top, just to help us out. And then our matrix is going to start on the next line, and it's going to be, so like here, and then it's going to be multiplied. The matrix we're multiplying by is going to look like this, or here. I'll just write them out. So it's V11 through Vm minus 1. Let's see here. Let me give myself an entire screen here. So V11 all the way through Vm minus 1, 1. Then we have V12 all the way to Vm minus 1, 2. We have V13 all the way down to Vm minus 1, 3. No. Yes. V13 through Vm minus 1, 3. And then we keep going. Eventually we'll end with V1 and then n minus 1, and that's going to go all the way down to Vm minus 1, n minus 1. And I have drawn horizontal lines here between each of the column vectors. But anyways, this is the vector that we're going to be multiplying, and then we have to figure out what our other matrix is going to look like. Oh, man, straight lines, they're not easy to draw. Okay, cool. So let's break this up into a grid. Let's see here. We've got like... Oh, if only there were like lines on this page that I could have used to help me like draw straight lines and everything. Probably could have used that to my advantage, but we'll make do with what we have. So we're going to write this in block form. And we really only need to figure out how these first two rows are going to look. So these like 5 blocks. Once we get these 5 blocks, we'll kind of see what the rest of the structure will look like. But what will this look like? So let's start with V12. So we can take V12, and if we look back at our equations, which I can't look back at now because I'm scrolled down here, corresponding with V12, well, let's see here. Basically, what I'm saying is I'm looking at this row here, this row that I have selected here with this arrow, and that row is going to correspond to F12. So we want to find what coefficients we need to put here to make this look like F12. So if we do that, let's see here. We know that there is a we got a 2 over h squared plus 2 over hx squared plus 2 over hy squared plus sigma and that's going to be the coefficient of V12. And so remember, I defined that to be alpha, so we're going to put in alpha here. Here, I can scroll up a little bit so that we can see the coefficients that I'm using. Okay, so we got an alpha there. And then what about our beta x's? So that's minus 1 over h squared, and those are the coefficients of, let's see, vi minus 1j and vi plus 1j. So vi minus 1j will, for this scenario, I is 1 and j is 2. So vi minus 1j is v0, 2. But because we have a 0 index, that's automatically 0, so we don't include that term. But as for the other term, we're going to have v22, and so that's going to go right here. So this is beta x. What about the beta y's? We have the beta y's will correspond to v11 and v13, and those are just here and here. So now let's think about the next row, the row corresponding with f22. So the next row down corresponding with f22. So we're going to have an alpha at v22, and then at v12 and v32 we're going to have beta x's. So those go here and here. Oh, of course, yeah, this is V21 and this is V23. Yeah, of course this works. Yeah, it's quite hot in my apartment. Anyways, so we see that this pattern here is going to continue throughout the rest of this matrix, and so when we get to the second from the last row here, we're still going to have beta x, alpha, beta x. We're going to have beta x going across here, and across here. And then finally at the end we have beta x. When we look at Vm minus 1 comma 2, well, there's we have the alpha that goes there. There's going to be a beta x that goes with Vm minus 1, 1. No, for the beta x will go with it will go with Vm2, but then, no, it will go for the beta x's. There's a beta x that goes with Vm minus 2, 2 and Vm2. So the Vm minus 2, 2 beta x has already been drawn here, but as for the Vm2 coefficient, well, Vm2 is equal to 0 because it's at the endpoint. So we don't include that beta x. But as for the beta y's, we still have those here. And we have them here. And then we look at the top two boxes again, and this actually is going to be very similar. We look at V11. Most things are going to drop out. The only thing we have is we have an alpha there, we have a beta x here, we have a beta y here. And you basically just apply the same logic as in the second row of the second box row, these three boxes that I have in a row here. You apply those to the first two boxes that I have up here, but the only thing is there's a whole bunch of other terms that aren't included because they're automatically 0 because you're at the boundaries. So this is again going to be beta x, alpha, beta x, alpha, beta x, and then beta x, alpha. I'm going to have this. So we're going to connect here. And then here we have beta y's all the way down the diagonal again. Okay, and you can also see that because of the way that we've constructed these matrices, the third row of box matrices is going to look, or block matrices, is going to look exactly like the second row of block matrices, but just shifted over a block. So it's going to be like here, you're going to have your block of beta y's down the diagonal, and right next to it you're going to have your alpha and your alphas and your beta x's as your tridiagonal matrix. Then if you were to go over one more, you'd have another block matrix of beta y's on the diagonal. And you can also convince yourself that the bottom row of block matrices, you'll have first a block of beta y's, and then you'll have a block of alphas and beta x's. And so that's that basically tells us how to set up this. That shows us how to set up our system of equations. Therefore, the system of equations can be written as follows. So we have A, and then we have beta y times the identity matrix I. Then we'll have A again here, beta y times I, beta y times I. Then this is going to continue down here. We're going to have beta y times I, A, and beta y times I. And then finally, we have beta y times I and then A. This matrix times, now we have V1, V2, all the way down to Vn minus 2 and Vm minus 1. And again, each of these Vj's is a column vector. So this is a really, so each Vj that I've drawn here actually contains n minus 1 entries. So this is, so the length of this entire vector is m minus 1 times n minus 1. And finally, on the other side of the equal sides, we have f1, f2 through fn minus 2 and fn minus 1. Is that right? Yeah, this should be an n here, n minus 1. Okay, and again, these f's are also column vectors. Okay, and so this is where A is given by, well, it's just what I had before, alpha, beta x, alpha, beta x, tridiagonal, beta x, alpha, beta x, alpha, again, here, come on, okay, and this is, how big is this matrix? So, this is m minus 1 times m minus 1. Because if you go back and you looked at the block setup, each block corresponded with one of the column vectors that we were looking at. And each column vector had m minus 1 entries, and so each block must be m minus 1 by m minus 1. Each I above has dimension also m minus 1 by m minus 1. And the block grid is m. No. No, this is right. The block grid should be n minus 1 minus 1 by n minus 1. Yeah, of course, because look, we've got n minus 1 row vectors here, and each row in each of these vectors corresponds with like a block, and so you look at this block matrix and it should have n minus 1 by n minus 1 entries, and each of those entries is a block matrix of size m minus 1 by m minus 1. So this matrix as a whole has n minus 1 times m minus 1 rows and also the same number of columns. And so yeah, that's how we set up this system of linear equations. If you look at this, you might notice that this is almost identical to what was given in the book for the same problem when it was ordered the other way. The only thing that changes is that this matrix A here that I have, instead of having like the alphas will be the same. Instead of having beta x's, you'll have beta y's. And then in the block matrix format, instead of having beta y times I, you'll have beta x times I. And then of course, each of these the column vectors, the vj's, instead of going from v1 through vn minus 1, it'll go from v1 to vm minus 1. And similarly, f1 through fm minus 1. And that's just because of how each of the vectors has n minus 1 entries. And then the block matrix, the block format itself will be m minus 1 by m minus 1. And each block in that m minus 1 by m minus 1 structure will have n minus 1 by n minus 1 entries. And so it's sort of like taking that format and flipping n and m, flipping x and y, and flipping I and j, the sub indices I and j. And that's sort of what you should expect, because all we're doing is we're just flipping the variables. And so yeah, that's how you set up this matrix. If you're doing a lot of numerical methods, then there's a lot of figuring out how, like, you take a system of equations, you discretize it. No, you take like a system of differential equations, you discretize it, and then you figure out how you're going to put this into a matrix. And so there's a lot of doing this kind of thing and constructing these kind of matrices. And so getting good at this is an important skill. And the way I showed above sort of helps. That row that I put of the vectors above was just to sort of help keep place and help me remember, okay, when I'm looking at this matrix, when an entry in this column gets multiplied by the corresponding vector, what element of that vector is it going to be multiplied by? So it was more just to help me see the grid structure and help me set up the matrix, but it might also be helpful for you. If it's not helpful, you can just ignore it. But anyways, that's about it. I am now done with the proof of this exercise solution.